Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
So I'm going to talk about a numerical optimization algorithm for solving the sparse least-square problem. It's joint work with Tong Zhang from Rutgers University. So this is a sparse least-square problem. It's just L1 regularized least-square problem. It has a classical least-square objective there. I have OK, yeah, here. And also a L1 regularization term.
That one doesn't work. It's the green button.
Here, A and B are the data, problem data, and the lambda is the regularization parameter. Let's look at a concrete example about sparse recovery. We have seen lots of talks. That's good for me. I don't have to explain too much. So basically, you have a signal x, which is sparse. The dimension n can be very big. And you make a m measurement. Here, we focus on the case m less than n. Each observation is a linear measurement corrupted by a noise z. So this is a basic generalization model. And so after observing B and knowing A, you want to recover the X. Of course, knowing that you want a sparse X, the convex opposition approach is just use L1 regularization. And they have lots of application. For example, in machine learning, you can think about regression with feature selection. You want a small number of features. And has lots of application in signal image compression, image denoising, in statistics like gene identification. And recently has lots of received lots of attention because of the compressed sensing theory. So lots of work addressing the property of the optimal solution to this problem. If you have the optimal solution to this problem, how well it will cover and what condition on A you can recover. But in this talk, I'm giving pure optimization talk, is how fast you can solve this problem. So this is the focus of this talk. OK, let's make the assumption is that, of course, m less than n. This is the say compressed sensing. You have less observations. And the solution, we assume that solution is sparse. Of course, otherwise, there's no point we use L1 regularization because we assume lambda is big enough, so you got a sparse solution. Let's look at this current numerical optimization algorithm for solving this problem. Here are at least 3 state-of-the-art algorithms. Here's the cost per iteration. All are iterative algorithms. This is the number of iterations they need. For reach epsilon-optimal, meaning that the objective function of that sparse least-square problem to within epsilon close to the optimal. And you can see that iterative point methods is really good in terms of iteration complexity, but each iteration costs a lot, especially when m and n are big. Actually, in practice, this is only theory you can prove. In practice, this is you can substitute this complexity with the constant, like say 100, and that's done. So it's really good. Of course, for large-scale problems, maybe your only viable approach is first-order gradient methods. Each iteration costs mn. You just do a matrix vector multiplication. And the iteration, the classical, I will explain what is Proximal-Gradient method in the next slide, is 1 over epsilon. And using this sort of accelerated techniques, it will get you 1 over square root of epsilon. So in this talk, we see for this particular problem, with some standard assumptions of sparse recovery, because this is the context we study this problem anyway. And our algorithm can basically combine the advantages of the first-order method and the second-order inter-point iteration complexity. So it's uniformly better than the previous algorithm. OK, before getting into the details, I will first give some discuss some background on convex opposition. Hopefully, it's not too boring. So terminologies, if I say a function is convex, we have this. So its epigraph is, has a supporting hyperplane, which is given by the gradients. Of course, it could be non-differentiable here. There's be multiple supporting heteroplanes. If I say a function is smooth, a convex function, I say if it's smooth, meaning that there's the blue one is the quadratic upper bound of the function. And with parameter L, for example, you can take L be the largest eigenvalue of your the hashing of the function if your function is differentiable. So this is smooth. And another one is strongly convex. Of course, I have to mention that here for this one, why it's called smooth? Because you cannot have the non-differentiable like kinks like this. Because you can imagine if you move this point, because this inequality has to hold for every point. If you move the point to here, then no quadratic upper bound will be an upper bound. So for strongly convex, you have a quadratic lower bound with parameter mu. So this is basic terminology I will use. Okay, let's consider more general setup called composite optimization. Use objective function has a smooth, both are convex, of course. This is a smooth part. This is, could be a non-smooth part, like L1 regularization. And for this kind of problems, we use so-called Proximal-Gradient Method. So basically, you start with some initial point, then you do an iterative algorithm. At each step, you calculate the gradient of the function of the smooth part. And here, this basically gives you a quadratic approximation. Indeed, it's a quadratic upper bound of your function. And then you just take the non-smooth part here without any change. It's just the approximation of your objective function. But good thing is that if the psi is simple enough, you can solve this in a closed form, so it's very easy. And for example, if psi equals 0, this just give you gradient descent. And for the L1 case, a solution given by this so-called iterative soft thread shooting. So basically, you first pretend you are going to do a gradient step with step size 1 over L, and then you take each component of this vector, go through this soft thread shooting operator. Basically, you want to shrink the magnitude. So by alpha, here you want to raise it because you want to shrink the magnitude. If it's larger than alpha, but it's within this less than alpha, then you just take it 0. So you can see that if the lambda is big enough, or alpha is big, you get a lot of zeros in your solution. So that's why you produce sparse solution. So that's the intuition of this method. But this is not very important for this talk. Let's just look at the computational complexity. Let's say with this smooth assumption, then the iteration complexity for finding an epsilon-optimal solution is for the proximal gradient method I just described is 1 over L. And again, for accelerated ones is square root of 1 over epsilon. Indeed, this is called optimal method, meaning that there's no first order methods can perform better on this class of problems. And so this is for smooth assumption. But now let's see what happens if we add another assumption. Say F is smooth, but also strongly convex, meaning that it not only have an upper bound, it also has a quadratic lower bound. Here, mu should be strictly larger than 0. In this case, the same algorithm without any change, we just use it, will give you this log 1 over epsilon convergence rate. So it's geometric, or you can call it linear rate. It's much, much faster. And the optimal method, again, you will make this constant smaller. Here, L over mu, we call it the condition number. This is the square root of it. So we call this is the optimal method. Again, optimal method meaning no other first order methods can be better. This is already the best you can get. Okay, now we have the enough background. Let's look at this L1 least square problem. So as I said before, we focus on the case m less than n. So M is kind of a wide fat matrix. So Fx is the least square, and then you can check the hashing is just A transpose A. You can see this function is all very small because it's just a pure quadratic function. And you take the largest eigenvalue of the A transpose A, this gives you the parameter for your quadratic upper bound. So it's good. For Taylor expansion, it's simply. But it's not strongly convex because the minimum eigenvalue is 0 since this shape is this rank M. It's not strongly convex. So that means we only expect sublinear convergence rate. Either this or that, depending on you use accelerate or not. OK, so that's the verdict from the theory if you check the function. But now let's look at what happens in reality. Here is just the randomly generated example with M equals 1,000, N equals 5,000. And here is a proximal gradient method and two different versions of the accelerated gradient method. As you can see, this is by the way, this y-axis is optimality, meaning how far you're from the optimal gap. And the horizontal is the number of iterations. As you can see in the beginning, the proximal gradient method is kind of slow. This is a log scale on the vertical axis. So this is a sublinear rate. And the accelerated gradient method is faster in the beginning. But if you stop here, you'll say, yeah, I should use accelerated gradient method. This is the best method. But if you just be patient, running a little bit longer, suddenly you found that there is a very dramatic change, very fast geometric convergence when you're getting close to the optimal point. But on the other hand, the other accelerated gradient method doesn't have this kind of phase. So you might wonder what's happening. Let's look at the number of non-zeros, the sparsity pattern of each iteration you get. Here is the sparsity, number of non-zeros there, and this is iteration. As you can see, this fast convergence happens when the number of non-zeros is very small, getting to, this is like 100 or 200 also. That's when you get really fast convergence. And although the accelerated gradient methods reach that level much early, it doesn't affect it much. But for this red line, you can see that when it hits the sparse solution, it actually slows down. But I still don't quite understand this one. But let's look at the proximal gradient method. So the observation is that it has slow global convergence, but fast linear rate when iterate gets sparse. And close to optimal, because close to optimal is very important because we start every iteration from the 0. This is very sparse, but it's just far from the optimal. You don't get fast convergence. Let's look at the reason. See, your solution. Assume your solution is really sparse, and without loss of generality, you can repartition the vector, permute the vector, so that this is a non-zero part, this is zero part, and you can this is your matrix how you singular generated. So you can say that only the an part is useful, and if you calculate the hashing, it's like this. Here, if you restrict your consideration, your problem into the subspace n, then first look at this. You could get a strong convex, local strong convex. Your minimum eigenvalue could be larger than 0. At the same time, your upper bound is getting much smaller. So that's another thing. 1 over L is your step size. You can go much faster. So if you're minimizing this problem, actually this is equivalent. If you had known the subspace ahead of time, you could solve it very fast. But unfortunately, you do not know the subspace ahead of time. So you have to think about a way to somehow adaptively to get close or finding the subspace. So here's Kim's idea. Based on these two observations, the idea of homotopy continuation. Homotopy continuation is a general method. So basically, you have a class of parameters by a single parameter, and the one you want to solve is very hard to solve directly. But if you vary the parameter from the beginning, it can be very easy, and you change the parameter a little bit. Use the previous solution to initialize your algorithm, numerical algorithms to solve the second one. You get faster, and then you do it. The overall complexity might be much faster. So here is what happened: is that you want to always engage in the sparse mode, fast local convergence. So the idea is that for this L1 regular square problem, if you give large enough regularization lambda, like this number can be easily computed, you will get a zero solution without any change. And then you just reduce lambda a little bit, tiny bit. You say, the solution is very, very sparse. But from that on, if you use the proximal-gradient method, you can just get in there like maybe very few steps. You will stay in the, you will always use this part of your numerical algorithm. And then you just reduce it a little bit, and then finally converge it. So the hope is that overall complexity is much smaller. And indeed, this is not a new idea. There's some works already using similar techniques, but superior performance has been reported. But the problem is there's no global complexity analysis. In order to answer that, you need to have answer two questions: how fast you decrease lambda, and also for each lambda, how accurate you solve. If you just solve to super accurate or just a few. Here is the proximal gradient method. You have two parameters based on that idea. So both of them are within 0 and 1. So you initialize your problem with this parameter, end up with a zero solution. And then this is the number. You reduce your lambda with a constant factor, eta. This is the number of outer iteration you need to run. And at each step, you reduce the lambda by a constant factor. And also, you saw it's a very low precision. Delta could be 0.1, for example, proportional to your regularization parameter. And then you solve it. And for the last iteration, of course, you see I require high precision epsilon. You could go for whole epsilon. But you are already in the geometric zone, so you are fast. Let's look at an example, the same example. Here is the previous result of this proximal gradient. Now, the black line is the homotopy. So this kind of stages is, as I said, each intermediate stage, you only need a very tiny, very loose precision. You can die in like 2 or 3 iterations. And you actually moving this geometric phase much earlier happening here. So you get a very, very fast performance in practice. OK, now we have seen all the ideas. I hope to give you some little bit technical reasoning behind it. Is we define restricted eigenvalue. So only define, this is the largest, the smallest eigenvalue on the vector with sparse support not larger than s. S is less than n. This is hopeful that if s is small enough, if your matrix A is behaving OK, good, then you will have this minimum eigenvalue larger than 0. OK, so let's remind us this previous picture. So it's just restricted eigenvalues, largest and smallest. The important is that the smallest one should be larger than 0. You got a strong convexity somehow. And here, precisely if the support of your two vector x, y, the union is less than certain sparse level s, which satisfies the restricted eigenvalue condition, then you will get this restricted smoothness. So this is quadratic upper bound, quadratic lower bound. If this is larger than 0, you got strong convexity, and you got fast convergence. Here is the restricted condition number on that in a sparse support. So our basic convergence analysis is basically assume, of course, m less than n. Your target lambda is sufficiently large. That means all your previous lambda must be sufficiently large. And then local convergence. If you start a sparse solution and also close to optimal, then proximal gradient has geometric convergence. The details are in the paper, so I'm not going to spell out the details. Overall complexity is that if delta and eta is both within 0 and 1, satisfy this condition, simple condition. Here, the delta prime is a parameter actually comes from the restricted eigenvalue condition. I'm not going to get details here. And then every stage of proximal gradient homotopy will have a geometric convergence. And your overall complexity is just m times n is your per iteration complexity. Your number of iterations is log 1 over epsilon here times the condition number. OK, let's summarize. Computational complexities for solving these sparse least-square problems as we talked before, this is the current state of the art. And the cost per iteration and iteration complexity, we have made both the best in different numerical algorithms. Here, of course, we are using some special structure of this problem. That this is a least square. This is a matrix. You have some restricted eigenvalue conditions. I believe for more general functions, the numerical algorithm should still work. Actually, we have did experiment. It worked well, but it's just much harder to give a kind of restricted condition, eigenvalue conditions if you have a more general convex function. And here are some extensions. As we have seen before, using accelerated techniques, it's possible to reduce this one to square root of the kappa. We have just finished this work with Qihang Lin from CMU this summer, but unfortunately, we have a hidden log factor there, log of the condition number. This is because the algorithm need to somehow, the accelerated gradient method need to know the mu. But in this case, we just don't know. We have to have an adaptive process to estimate unlengthed mu to achieve that. That will cost you log kappa factor. And maybe some extensions to fast low rank matrix recovery, as what Miriam talked. And actually, Miriam and his students, Reza, is currently working on this. OK, thank you.
Any questions for the speaker?
Of course, now you have to, in addition to lambda, choose the eta as well, right? So
which one?
Like you have to choose the parameter with how fast to decrease your lambda now, right? So
yeah.
You'll have to make multiple rounds.
Yeah, but eta, delta and eta. This but let me tell you this. So this is a theoretical analysis. In practice, we did experiment. All the delta and eta, so if you run the best performance, always doesn't satisfy our restricted eigenvalue condition, always violates our condition. The reason is that for the homotopy algorithm to work, the most important thing is you want to make sure your final stage, which has precision, you reach the final stage in the local restricted convex mode. Before that, every stage has a very low precision. In that regime, either a sublinear rate or linear rate, it's not clear linear rate will be faster than the simple gradient algorithm. So it's not, in practice, that's not important at all. The important is you want to bring your final stage in the local convergence. So in practice, to answer your question, the parameters choice is you can be much wider than what the theory predicts.
Any other questions? OK, thank you, Lin.